So now finally, okay, once you understand the concept of heat transfer, we can touch this cycle called the refrigeration cycle or vapor compression cycle. There are two names for it. So just now I mentioned, okay, you have a compressor. Okay, why do we suddenly talk about pressure? Okay, all along we are talking about temperature, low temperature, high temperature, and heat transfer. Why suddenly we introduce an additional parameter called the pressure? Okay, because pressure actually affects temperature. Okay, pressure and temperature is correlated. So pressure and temperature, okay, they are correlated. So if you notice, let's say you go and climb a mountain, go to a place with very high altitude, okay, you will notice that the higher you go, the lower is the temperature. You will just get colder and colder and colder. Why is that so? Okay, it's because the higher you go, the lower is the pressure. Okay, because when you're far away from the center of the earth, okay, pressure will reduce. When pressure reduces, temperature will reduce at the same time. Okay, so they are correlated. High pressure, you will have high temperature. Low pressure, you will have low temperature. So these two guys, okay, notice that, and in order to produce cold air, what must you do first? Okay, you have to create a region of low pressure. Okay, then low temperature will come together with it. So to achieve this high pressure and low pressure, you can use that device that we mentioned just now, which is the compressor. Okay, compressor is able to generate a region of high pressure and low pressure. So you can imagine the inlet of the compressor will be cold. Okay, the outlet of the compressor will be hot. Okay, so you create this artificial region of cold and hot region. Instead of everything the same temperature, because of thermal equilibrium, you are able to separate the coldness and the hotness simply by using a compressor. Okay, so now let's go to this very, very important cycle, okay, the refrigerant cycle, which I will need to explain in details. Okay, so this cycle, right, it consists of 4 components. Okay, if you look at the diagram, there are 4 components, namely the compressor, condenser, evaporator, and another thing called the expansion valve. Okay, so let's start from point 1. Okay, the top left-hand corner, point 1. We call it the compressor inlet. So what is actually flowing inside this cycle, right, is what we call refrigerant. Okay, refrigerant, or sometimes in common terms you call it gas. Okay, but it don't always exist as a gas. Okay, that's the thing. Okay, we just call it refrigerant. So at point 1, the compressor inlet, okay, it is where the pressure is the lowest. Okay, as I mentioned just now, compressor inlet, lowest temperature. So it will have a low temperature, low pressure, and at the same time, low temperature. So what happened when it passed through the compressor? Okay, so now here, low temperature, low pressure, pass through the compressor. What will happen? Okay, the pressure will increase. Okay, pressure will increase. When pressure increase, as we know, they are related to temperature, so temperature will also increase. Okay, so that is when you have a high pressure, high temperature region. Okay, now imagine the refrigerant is very hot now. Okay, the refrigerant is now very hot. You need to cool it down. Okay, you must remove the heat from the refrigerant. How do you do that? Okay, you pass through a heat exchanger, and this heat exchanger, we call it condenser. Okay, condenser. So condenser is simply just you see it's like a cooling coil. Okay, it's a coil. Okay, and you have a giant fan. Okay, you have a giant fan that is blowing across the coil. So imagine a refrigerant is slowly flowing across the condenser, and you have a fan that is blowing cold air. Not exactly cold air, but the ambient air. Okay, because the temperature right now maybe is around 60 degrees Celsius. Okay, and our ambient air is maybe around 30 degrees Celsius. Okay, our outside air. So what will happen, as we know, heat will naturally flow from hotter region, which is the hot refrigerant, to the colder region, which is the cold outside air. Okay, so now you know why, right? The condenser, when you switch on your aircon, when the condenser is working, you will notice hot air will come out from the fan. It's because it is trying to cool down the refrigerant. That's why the air that comes out from the condensing unit is always hot. That's the main reason. Okay, so now the refrigerant is being cooled down. Okay, it's cooled down maybe to around 45 degrees Celsius. Okay, so let's say just give it a number, maybe around 45 degrees Celsius. Okay, so the temperature drop. What will happen? Okay, so the refrigerant will continue to flow, and it will pass through this. Okay, so point number 3. Okay, so okay, let's go back to this. When the refrigerant get cooled down, right? Okay, it's not only the temperature will drop. In fact, right, it will get condensed because over here your refrigerant exists as a gas. Okay, your refrigerant is a gas. So when a gas get cooled down, what will happen? Just like if you have a steam, okay, hot water, when you heat to 100 degrees Celsius, it becomes steam. And when you cool down the steam, it will become water. Okay, so which process actually takes place is condensation. Okay, that's why this region is called a condenser. Okay, because condensation takes place over here. So from gas, it become a liquid. So your gas get cooled down, okay, and undergo change in phase, okay, and finally it become liquid. Okay, it condenses to liquid. So now this liquid will flow, and it will pass through this device. Okay, so what is this? This is actually an expansion valve. Okay, the diameter of the pipes, right? Okay, of the tube over here will suddenly change. Okay, there will be a change in diameter. So it's to create a constriction, and what will happen? Because of this constriction, right, it will cause a sudden drop in pressure. Okay, this device, the main purpose is to create a sudden decrease in pressure from a high pressure area, maybe 2 megapascal, drop all the way to 500 kilopascal. Okay, so it will create a decrease in pressure. Okay, a decrease in pressure. And as we know, when pressure becomes very low, what will happen? It will become very cold. Okay, the whole refrigerant now is very cold now, maybe around 4 degrees Celsius. And this is what we want. Okay, the 4 degrees Celsius refrigerant is what we want, because we know that the cold refrigerant is able to go to your room. Okay, go to your room, and there will be a fan. Similarly, there will be a fan over here that will blow across the cooling coil. Okay, and what comes out is your cold air. Okay, and that is your aircon. Okay, the cold air that actually comes out from the box is actually happening over here, the evaporator. Okay, so similarly, just now when it passes through the condenser, your refrigerant loses heat to the surrounding. Okay, but at the evaporator, okay, it actually starts to gain heat. Okay, your refrigerant is gaining heat from the air in the room. Okay, so your refrigerant will get heated up. Okay, so remember when a liquid, right? Okay, over here is still a liquid. Okay, maybe liquid plus gas mixture. Because when it decreases in pressure, right, some of the liquid will become gas. So it's a mixture now, maybe 80% liquid, 20% gas. And when it starts to gain heat, just like when you boil the water, okay, it will start to evaporate. Okay, it will start to boil off. Okay, so evaporation will take place, it will become gas again. Okay, so that completes the cycle. So it will become gas again, and it is a low pressure, okay, low pressure and low temperature gas. Okay, although it gains heat, but it's still relatively low temperature, maybe around 20 degrees Celsius. Then the cycle will repeat. Okay, the cycle will repeat. You will pass through a compressor again. And so this is the vapor compression cycle, and the most important cycle you need to know for this particular topic. Okay. So, in actual, okay, how does all this thing look like? How does all this component look like? Okay, so evaporator, as we know, is actually your fan coil unit, okay, the box that is in your room, okay, the cold region that's absorbing the heat, okay. Whereas for the other three components, is all housed inside this condensing unit. Okay, your expansion valve, your compressor, your condenser is all housed inside this unit. That's why this particular item is much more expensive, or it's much more easier to break down, okay, because there are three components inside. So you may ask yourself this question, okay, why do we want to always target the change of phase? Okay, what is change of phase? Change of phase means either from liquid to gas, gas to liquid, okay, solid to liquid. So when there's a change in state, for example, ice to water, water to steam, okay, when there's a change in state, we call it change of phase. Okay, why do we use change of phase over here? Okay, from gas to liquid, and over here, from liquid to gas. Okay, the main reason is because the latent heat, okay, latent heat is much bigger than sensible heat. So what is latent heat and sensible heat? Latent heat, right? Okay, so let me explain this term. Okay, what is latent heat? Latent heat, it means the amount of heat you need to absorb in order to change a state. For example, when you have a 0 degree Celsius piece of ice, okay, 0 degree Celsius, to 0 degree Celsius puddle of water, okay, temperature don't change. Okay, the temperature remains at 0 degree Celsius, but this is 100% solid, this is 100% liquid. Okay, so how much heat is needed to convert this piece of solid to this amount of liquid? Okay, that is the latent heat. Okay, similarly, water at 100 degrees Celsius, okay, let's say water at 100 degrees Celsius, to gas, okay, to your H2O gas molecules, okay, at 100 degrees Celsius. So again, there is no change in temperature. Okay, you are boiling off all the water to gas. How much heat is needed? Okay, that is called the latent heat. So this is called latent heat of vaporization. This is called latent heat of fusion. Okay, then you may ask, how much heat is needed to increase a temperature from 0 degrees Celsius to 100 degrees Celsius? This is what we call sensible heat. Yes, sensible heat. So if your heat, when it's absorbed, right, it causes a change in temperature. Okay, it causes a change in temperature, be it from 0 to 100, 0 to 10, 10 to 20. Whenever there's a change in temperature, okay, that is called sensible heat. Okay, whenever there's no change in temperature, instead change of a state, okay, it is latent heat. Okay, so the amount of heat actually need to convert 1 kg of water, okay, 1 kg of water to 1 kg of steam, okay, is called latent heat of vaporization. Okay, that is this process over here. So if you notice when you want to cook something, you take a pot of water and you start to heat it up at, over the gas cooker. Okay, it may take only around 3 minutes to 4 minutes, okay, for your water to start to boil. Okay, but if you, let's say, you forget to off the stove, okay, and you let the water continue to boil, okay, it will maybe take around another 15 to 20 minutes, okay, before you start to boil off everything. So that's the difference. So you notice that, okay, because latent heat of vaporization, right, is always much higher than sensible heat, okay, the sensible heat. So that's why we want to use this process at these two parts, okay, when it's absorbing heat and rejecting heat, okay, we want to target this property of the gas, okay, because it will be able to absorb a lot of heat and is able to reject a lot of heat, okay, instead of causing a change in temperature. So let's say if you go back to this cycle, okay, the amount of work done, right, okay, is actually at the compressor side. How much work is being done, how much you compress it, okay. The amount of heat rejection, is at the condenser side. Okay, in short we call it Q con. Okay, Q is the general symbol for heat. Okay, so if you have a subscript of COND, it means amount of heat rejected at the condenser. Okay, so for the evaporator, we call it Q evap. Okay, this is the amount of heat you absorb at the evaporator. So together with work done by compressor, how do we relate these three? Okay, how do we relate these three parameters? Okay, so if let's say we go back to the first law of thermodynamics, okay, we know that the amount of work done, okay, the amount of heat you put into a system plus the amount of work done on the gas compression process is equal to change in internal energy. Okay, for a closed loop system, in this case, vapor compression cycle is actually a closed loop system. So for a closed loop system, right, there is no change in internal energy. Okay, so this is 0. What is Q? Okay, Q is the amount of heat that enter the system. In another word, is the amount of heat you absorb minus the amount of heat you reject. Okay, so Q, it become Q evap, the amount of heat you absorb minus the amount of heat you reject. Okay, so that's Q. What is work done on gas? Work done on gas is just work done by the compressor. Okay, the work done by compressor. So if you rearrange this equation, you will get Q condenser is equal to Q evap plus work done by compressor. So in other words, okay, the amount of heat you reject at the condenser, right, is actually the amount of heat you absorb inside a room plus the amount of work done by the compressor. Okay, so in other words, the amount of heat you produce, right, is always higher than the amount of heat you can absorb. Okay, so the missing word over here is sum. Okay, so the amount of heat rejected at the condenser is the sum of the heat you absorb at the evaporator and the work done by the compressor. Okay, the last part of this topic is on refrigerant. Okay, so as I mentioned just now, what is flowing inside the vapor compression cycle is actually what we call gas or coolant, or the official term is called refrigerant. So you may heard of all these refrigerant like R22, R134A, R123. So some of the in the past, okay, we actually use this compound called CFC, okay, chlorofluorocarbon, inside the vapor compression cycle because it has very good properties, okay, but because it's very bad for the ozone, okay, that's why it's being phased out. So now it's being replaced by all this, which is the HFC, hydrofluorocarbon, which is better in terms of to the environment. Okay, so why do we use refrigerant in vapor compression cycle? Why don't we just use water, which is very environmental friendly? Okay, because water can also evaporate, water can also condense. Okay, but because the main reason is because water don't have the suitable thermodynamic properties. Because if you want to achieve the kind of temperature, your compressor will have to work 30 times harder. Okay, you will need to have a very big compressor in order to achieve that low pressure, low temperature. Okay, which doesn't really make sense. Okay, you will consume a lot of electricity. Okay, so refrigerant are chosen because they have suitable thermodynamic properties. That is, they will boil at very low temperature. Okay, maybe around 40 degrees Celsius they will start to boil, compared to water, which only start to boil at around 40 degrees Celsius. 100 degrees Celsius. Okay, and they are also able to absorb a lot of heat when they are boiling. Okay, so when they can absorb a lot of heat, it's able to absorb more heat from the room or whatever place you want to cool down. Okay.